Oh, it would help if I hooked up the HDMI. Hold on. Let's try that again.
It's what? It's not bad.
It's the third one.
There we go.
This the first one. I was like, the first one? I was like, the first one? So, the second one I did wrong, but by myself.
All right, let's get started. If you haven't already grabbed a handout, please do so. We're going to reference it today, although this handout is available on Blackboard, so there's nothing I'm giving you a hard copy of that you don't have available. And this random dollar figure that I have drawn on the board will make sense a little bit later, okay, and you'll see what I mean. Okay, how did the truss deflection homework go? Good. That is your last homework until next Wednesday. Because we celebrate on Monday. We have an exam review on Friday. We celebrate on Monday. Okay? So on Friday, what we will do is we will go through the format of the exam. I'll go through what's on the exam, which basically everything from day one up until the last lecture and the last homework is on the exam. So today's topic is not on the exam, but today's topic is different because we're talking about our class project today. Okay? So, all right. Any questions on logistics? The 3.4 is being graded. Other than that, everything's graded, and the solution for homework 4 will be posted on Friday. Okay? Any questions? Okay. Did everybody get the code?
I did not.
I don't think you got the code, given the fact that you just walked in. All right. So can you get the code? All right. Okay. If you have not yet grabbed a handout, there's a handout up here next to Mr. Allen. Raise your hand, Mr. Allen. Okay. So then right over here next to him. So we will reference that here in a bit. Okay. Let's talk about your class project in this course, okay? I started doing this class project about 4 years ago. I had been averse to doing class projects mainly because I thought it took away from just time in class. But I decided, you know, what the heck, let's go ahead and include one in. And if you ask students that have had this class before, most of them will tell you that this project isn't very bad, and in many ways it's a lot of fun. So, which is really my primary goal. Let's talk about my goals for the project. I told you before that part of the ways I developed my teaching philosophy is I just made a list of all the stuff that bugged me that professors used to do when I was in college. I said, I'm not going to do that anymore. Or I'm not going to do that when I'm a professor. And so that sort of applied to this. So my first two goals for the project is I wanted the project to be broad enough in scope that it would allow you all the flexibility of tackling the project your own way. And what that means is arranging the truss to be analyzed and designed. But I also wanted the project to be narrow enough in scope that you knew what you needed to do at the end. It did always bug me when I was a professor, when I would get a project and I would never really know what I was supposed to do and what I was supposed to deliver, because it was just, do this, and there was never much clear direction. So I want you to have the flexibility of doing what you need to do, but I want it to be narrow enough that you know what you need to submit. I want you to get a taste of system level design. What that means is designing a system to assess both strength and service limit states. And you'll kind of understand what that means as the project moves on. I want you to be able to use different software packages to assess a real world challenge. And we are going to we're going to use at least 3: Excel, Masthand, But our third software package and my other final goal for the project is I wanted to force you to use some CAD again. Yeah, you're engineers, you need to use CAD again. So to that effect, I just want to make a point about something. If you go to Blackboard and you go into student preview, so if you go to the analysis project, you're now actually going to see the link for the first submittal, which we'll look at here in a bit. There's the notes for this lecture today. The supplemental files I'll talk about here in a bit, but there's also instructions for installing AutoCAD if you don't have it installed yet on your personal machine, which you should, but if you need to redo that, there that is. Okay. Okay, so big picture, what's the goal? Our goal is to lay out and detail a pedestrian truss that's going to connect this building to the biotech building across the way over here, okay? So it's very much like the walkway truss that's over 3rd Avenue, the one that's right over here, the one that carries traffic from the science building over to the biotech building. You're going to do a similar truss that connects this building to this building, okay? That's your goal, is to design a truss bridge that will connect those two buildings. Make sense? Okay. All right, so in order to discuss this, I'm actually gonna kind of walk you through almost like how to do the project. But in order to do that, I want to talk about some relevant background. And so I mainly kind of need to focus on two things. The first thing I need to focus on is what's called system loading and this idea of tributary area, which will make sense here in a bit. The other thing I need to focus on are rolled shapes, AISC shape databases, and how you, like if I say W27 by 129, what that means, okay? So we're gonna take a little bit of time talking about background, and then we'll get into some details. Okay, so one of the things that we haven't yet talked about in this class is if I give you a beam with a 20 kip load and a 2 kips per foot distributed load and whatever, where do those loads come from? We talked about it a little bit, but like, let's dig into that a little bit. Where do those loads actually come from? Well, structural loads are commonly defined not not by like singular loads. They're commonly defined by uniform loads in sort of a pounds per square foot fashion. So like, for example, if we're talking about dead loads on floor systems, things like, okay, the metal deck pan that serves as the formwork for the concrete might be, 2 pounds per square foot considering the dimensions. If we're using normal weight concrete, it's going to be 12.5 pounds per square foot per inch of thickness. So if you had a slab that was 3 inches thick, then the slab would weigh 37.5 pounds per square foot. Does that make sense? Floor finishes. If we had tile floor, that'd be 10 pounds per square foot. If we had, what about the suspended ceiling, right? Because these floor beams have to hold that up too. Well, that's about 2 pounds per square foot. What about MEP, mechanical, electrical, plumbing, and allowance? That's got to be another 5 to 10 pounds per square foot, right? So typically we're specifying loads on floor systems in a pound per square foot basis. That's not always the case. Sometimes, like for example, with live loads, we might have a uniform load and a concentrated load. Or, in the case of, in the case of office buildings, you might have a storage location that's going to have a lot of file storage and a lot of heavy load. But typically, you'll spec those out in that fashion. Dead loads are sort of the self-weight of the structure. Live loads are related to its occupancy. So, for example, office buildings are going to have different live loads than hospitals. Hospitals are going to have different live loads than libraries. Libraries are going to have different live loads than theaters, and so on and so forth, right? So the idea is that we look that up. Okay. For this project, I'm going to give it to you, but you'll see what that means. Now, how do we actually take this pressure load, this 20 pounds per square foot, this 50 pounds per square foot, or whatever, and turn it into a beam with a triangle and a circle and a load that we can start doing structural analysis with? And the most common way of doing that is to use what's called tributary area. So tributary area is best defined as on a structure. If we're talking about, let's say, floor beams in a building, the tributary area for a given floor beam is how much area of the floor that beam is responsible for holding up, okay? And it is typically defined as the area bounded halfway between adjacent beams, right? So for example, okay, so I'm standing right here, there's a column right there, and so let's say there's a floor beam going like this, right? Okay, and let's say right here, there's another floor beam going like this, and maybe over there, and so on and so forth, right? So if I was trying to define the tributary area for this floor beam, it's commonly defined as halfway over to this floor beam, halfway over to this one. That area is what this floor beam is responsible for, right? Then anything past that, the next floor beam takes over, and so on and so forth. Does that make sense, that idea? Okay, so the idea is that we can use this to perform what's called a load takedown, okay? So let me kind of give you an idea. Does anybody recognize this picture, or where this picture would be taken from? This is from the 3rd Avenue parking garage, right down there, right? Okay. Now, the 3rd Avenue parking garage uses these pre-top double T's to act as floor beams to support the traffic load from all the cars parking in the garage. The idea, though, is that but for the purposes of this discussion, I'm going to treat each one of these sort of ribs right here, I'm going to treat each of those as a single beam, okay? Does that make sense? So I propose that if I were looking at, let me take my keyboard off here. If I propose, let me move this here. If I was looking at this floor beam right here, I propose that it would be responsible for all the shaded area right here, and I don't know, maybe like all the shaded area like that, maybe like this, that shaded area of the floor is what that beam is responsible for, right? Anything over here, this beam's going to be responsible for, right? Anything over here, like this beam's going to be responsible for. Does that make sense? So, so how do I use that? Okay. Well, here's how I use it. Okay. So let's say that I have a floor plan. Okay. So what we see here is sort of, imagine like being in a helicopter looking down at a building frame. Okay. So what I would see are these sort of like little squares or eye shapes or what have you right here representing the columns. And then I would see a series of, you know, skeletal frame members going up, down, left, and right, acting as beams and girders, right? Everybody with me on that? So let's just throw some dimensions here. Let's say, and I'm just making these up, okay? Let's say that this dimension here is 30 feet. I'm just making this up, okay? And let's say that between beams, let's say it's 10-foot spacing between beams. It doesn't matter, I'm just making this up, okay? So far so good? All right, and let's say that I want to look at an individual floor beam. Let's say I just want to look at this floor beam right here, okay? So I propose, I think that's the one that I pointed to, that the tributary area for that floor beam is going to be like that, right? Okay. Now, how wide is this? How wide is that? 10 feet, right? Because it's 5 feet this way, 5 feet this way. So far, so good? Now, let's say that I put 20 pounds per square foot on this floor system. Let's just say I put 20 pounds per square foot. All right? So I propose that 20 pounds per square foot, if I have a floor beam with that pressure load, right? It's got a pressure load everywhere. Oh, what happened? So don't get upset at me there. Okay. If I had a beam with a pressure load on there, then I propose that I could convert that into a floor beam with just a uniformly distributed load by taking that 20 pounds per square foot and multiplying it by 10 feet. In other words, like if the entire floor system sees 20 pounds per square foot and the tributary width is 10 foot wide, then along the beam, every foot, the beam is seeing 200 feet or 200 pounds. Does that make sense? So I could take that floor beam and say, okay, this is 200 pounds per foot. That floor beam is, what, 30 feet long? And suddenly I have a problem that I can analyze using the stuff I learned in Dr. Mike's CE 312 class. Do you see what I mean? So the idea is that I can take a real world floor system and just take the pressure load, multiply it by the tributary width, and by golly gosh gee, I come up with something that's very familiar. Make sense? All right, so I'm just curious, if it's 200 pounds per foot over 30 feet, that's a total of what, 6,000 pounds, right? 6,000 pounds means the reactions to each of these, the reactions on each side is what? 3 kips? Make sense? Everybody with me on that? Okay, so let me ask you this. Here's the floor beam. Where do those react? Okay, so here's the floor beam. So there's a 3 kip reaction here and a 3 kip reaction here. Where do those reactions go? Do they just like vanish? Or do they go somewhere? Like if I have a floor beam out in space, what's it connected to? These heavier elements right here, right? Okay? So looking at the beams, I've got something like this, but looking at the girders, let's say if I was looking at this girder right here, well, that girder is going to see 1, 2, 3, 4 point loads, 1, 2, 3, 4 point loads. And where do those point loads come from? The reactions here. Does that make sense? That's the idea of a load takedown, right? Then the idea is, well, I could find the reactions to these girders. Where do these reactions go? To the columns, right? So you like to go from the beams to the girders to the columns to the ground. Load takedown. Does that make sense? Everybody got the idea? You're not going to have to do anything that complicated for the project. I just want you to kind of get the gist. So far, so good? Okay. I want you to keep that idea in the back of your head, because the other idea I want to talk about are hot rolled products. Specifically, I'm talking about steel. Okay? Hot rolled steel is, for the purposes of construction, is typically produced in 2 fashions. The first is with like what I would call simpler products, like plates or bars, and then from those plates and bars, we would fabricate those into plate girders, connecting elements, gusset plates, you name it, right? We can do anything with that. But for building construction, most commonly we'll use rolled shapes. Things like channels, angles, T-shapes, and I-beams. We don't really use the term I-beams anymore because we have various classes of shapes that have an I-shaped configuration. For example, we have ones that are used primarily for beams and columns, which we call W-shapes, or wide flange. We have HP shapes, which are primarily used for piles, okay? So we have different shapes that are used for different purposes. Primarily, the most commonly used shape in American building construction is the W shape. And so if we're looking at W shapes, let's just consider a W27 by 129. Now, the W refers to the classification. So a W27 by 129 or a C15 by 50, right? And so that letter just refers to the shape classification. Does anybody remember what the 27 and the 129 stands for? What does the 27 stand for?
Flange width.
Not the flange width. You're on the right track there.
Width.
What's that? The width. Yeah, so the 27 is about how deep it is. And I say about, this handout that I gave you all, you can kind of see this. That handout primarily lists W12s. And if you look at the depths, they change a little bit. Some of the really heavy ones have depths that are much bigger than 12. But on average, W12s have about a 12-inch depth. And so W27s are going to have about a 27-inch depth. Now if that's the 27, what's the 129 mean? Weight per foot. So 129, the 129 means that if I had a W27 by 129, every foot it would weigh 129 pounds. Okay? So the bigger that number is, the heavier it is, right? Now, why does that matter in design? Because we buy steel on a dollar per pound basis. So if you're designing, you more often than not want this number to be as small as possible. Does that make sense? Within reason. And when I say within reason, take steel design. We'll talk all about it. Okay. So far, so good? Oh, that's not what I wanted to do. Let's do this. There we go. Okay. The only shapes that aren't named this way, which isn't really going to matter for us, are angles. And for angles, like they sort of are named like this. The first two numbers correspond to how long this leg is and how long that leg is, and then the half is how thick it is. But we're not going to use angles for this project, so for our purposes in here, it doesn't really matter all that much. Everybody good to go? Okay, with those two ideas in the back of your head, this whole tributary area idea and then naming conventions, let's talk about this project. And I'm actually going to go through a representative exercise for you to truly kind of show you how this works, okay? So we're going to go through a representative exercise, and I'm going to give you some parameters right off the bat. We're going to lay out a truss together for a bridge 60 foot long. Spoiler alert, the one that you all are going to do for your project is not 60 foot long. It's different. And I change the project parameters every year so that you really can't use a project from last year. So, but we'll get to that here in a bit. Okay. We're going to assume that the bridge is 24 feet wide, and I'll show you an image of what I mean by that here in a bit. But the idea is that the bridge, from here to here is 24 feet wide. Okay. We're going to put a pretty big load on this bridge. We're going to put a load of 1,400 pounds per square foot. Again, that's a really big number, okay? But I'm going to throw a couple of, ideas behind that number to sort of temper that a bit. The first thing is that we're going to assume that that number accounts for not just the live load, which is the people on the bridge, but also the dead load, the self-weight of the structure itself. So you aren't going to have to account for how heavy the members are during design because we accounted for that by assuming that in our load. The other thing is that we've also incorporated all of our factors of safety. Y'all know what I mean when I say factors of safety. So if you want a factor of safety of 2, you don't design the beam for 100 kips, you design it for 200 kips. You double the load and design it for that, right? That's kind of the idea. So all the applicable factors of safety, all the dead loads and the live loads are baked into this number. So yeah, it's really big, but the idea is now we can just use it and do the math, okay? Okay, for our design and for our bridge, we're going to employ the following limits. The first thing is that we're going to limit the selection to W12s. It's almost like I had this planned out when I gave you this handout, right? We're going to limit the axial stress on each member to 36 KSI, so we're going to break out a little bit of that engineering 216. And the mid-span vertical deflection is going to be limited to 2 inches. So we aren't going to be able to deflect, the bridge isn't going to be able to deflect any more than that much, okay? The other thing I'm going to give you is a cost per pound of steel. And we're going to say it's $1.40, okay? That's also a number I change every year, okay? So far, so good? Okay. Now, here's going to be our process, okay? The first thing that we're going to do is we're going to use all these constraints that I gave you, 60 feet long and so on and so forth. We're going to lay out the truss. And for the calculations that I'm going to do in here, this is a really, really simple truss, okay? We're going to use tributary area to figure out how much load goes on each truss joint, and then we're going to analyze that truss, okay? Then we're going to select members based on the stresses that those members see, okay? And the reason why that's important is because once we've selected members, then we know the area of each of those members and we can check the vertical deflection limits, okay? Now, more often than not, what's going to happen to you all in your project is you're going to get to this point and you're going to find that the bridge fails, that it's going to deflect too much. So we're going to have to iterate the member selection to get a truss that actually works, okay? And then once we get that, we compute the cost, draw it up all day, every day. Make sense? All right, everybody okay on this? All right, now what I'm going to do for our calculation and for the parameters in this, for this example, is I'm going to use a bridge that looks like this, okay? So there's a truss over here, a truss over here, and it's this distance that's 24 feet. So this is 24 feet. Okay, that's what we're going to use. Okay, now when we do the calculations, we're only going to focus on one truss because the idea is that this truss and this truss are going to be identical. So when it comes on, when it comes to member selection, when it comes to cost calculation, just give me the cost of a single truss. You don't have to double it to get both of them, okay? Because it doesn't matter, okay? So is everybody clear on that? Just one truss. All right. So far, so good? Okay. So here's my truss. Again, 60 foot long. I'm using 1-to-1 slope ratios, so we'll just say it's 10 foot high. So this is 1-to-1, 1-to-1, 1-to-1. Just again, trying to keep it simple, okay? But here's my truss. How do I analyze the truss? Well, in order to analyze the truss, I need to load it, okay? So how am I going to load it? Okay, so let's take my truss, okay? So the pressure load is 1,400 pounds per square foot, and then the bridge width is 24 feet, okay? Now each of these joints is 10 feet apart. So let me show you what I'm going to do here, okay? Okay, what I'm going to do is take, let's say, this truss joint. It doesn't matter, you can pick any one of them. And let's see if we can sketch out the tributary area, okay? Now I propose the tributary area is going to be halfway here, halfway here. And so this is what this truss joint, this is going to be responsible for. Like the load from all this floor is going to go here. And that's going to continue until we get halfway over to the truss. So if we want to solid this in, that this is sort of the tributary area for that joint. Does that make sense? Okay, so help me out. What's that dimension right there? What is this dimension?
10 feet.
10 feet. What is this dimension?
12.
12 feet. Okay. So 10 feet, 12 feet. Okay. So the tributary area is going to be 10 times 12 or 120 square feet. Everybody okay with that? You need to understand how to do that because that's going to be different for everybody in here, depending on how you lay out your truss. Okay. Now, how much load? What was the pressure load? 1,400 pounds per square foot. So if I take the pressure load times this area, I'm going to get 168,000 pounds or 168 kips. Does everybody see that? Now again, that's going to change for your bridge, for your bridge, for your bridge, for your bridge, for your bridge. It's going to be different, okay? Because you're going to have different loads. You're going to be spacing your joints out in a different fashion. Okay. Is everybody with me on this? So would you agree that, well, hold on. Let me go here. Would you agree that that's the structure I need to analyze? That makes sense? Now, a couple things I did skip over. Let me go back because I did skip over a couple things. Hold on. Okay? I did this for one joint, but would you agree the calculation is going to be the same for every one? Because the spacing is equal. If the spacing is not equal on your bridge, you're going to have a different calculation for each joint. That's not to say that's not possible, and it's not even that hard, just keep that in mind. The other thing that some of you might be thinking about is, what about the joints on the end? What about the tributary area here, 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 and here? Well, we're going to assume that all that load's just going to go right to the foundation, and it's not actually going to go to the truss, so we're just going to neglect it, okay? So I propose that this is the truss that we need to analyze, right? So what do? Take this truss, compute the reactions, do a method of joints, by golly gosh gee, right? That should be doable, right? Now, are you going to have to do this by hand? No, because you're going to do this in software, okay? But you could if you want, right? Make sense? Now, one thing worth mentioning is that I configured this truss very specifically to have one zero force member in the middle, okay? Because you might have a zero force member in your truss, and I want you to know how to handle it, okay? So far, so good? All right, before I move on, are there any questions? Okay. Now, what do we do with these axial loads? Well, what we do with these axial loads is we can start selecting members, okay? Now, for the purposes of our discussion, I'm just going to pick a random member, and I'm going to pick member HI, okay? Now, how much force is member HI experiencing? 672 kips in compression, right? Okay. So let's go through how to select our truss members. Remember, we're limiting to W12s, and we're limiting to a stress of 36 KSI. So do you all remember from mechanics, remember this? Remember that whole sigma equals P over A? So if you know sigma and you know P, take P and divide it by sigma and you can get the required area, right? So that's what we've got. So member HI. Member HI has a load of 672 kips. Chug it out and we get an area of 18.67 square inches. So my question to the class is, here's the list of all available W12s. What is the smallest or the lightest W12 that we could use for member HI?
65, is that right?
A W12 by 65? Yes. By the way, you can ignore the little F's, the notes. It refers to a thing at the bottom. That's a very CE 414 consideration. I'm not worried about that in here. Okay. Besides, it wouldn't really matter here because we're not bending the member. But does everybody kind of get the idea? So watch this. So would you agree for this member we can pick a W12 by 65? So what do? We just do that for all the members and we get this. Now, the central member was a zero force member. In the case of a zero force member, I just go with the tiniest one. Okay? I gotta put something there, so we'll just put the smallest member there. So far, so good? So what do I do now? Okay, I've got the truss members picked out. What's left? Deflections, right? What did we say the deflection limit was on this bridge? 2 inches. So what do? I do that analysis, right? Put a single load there in the middle, do my reactions, solve my truss, right? I mean, you all know how to do this now, right? So we don't need to go through the steps. Compute deflections using the method of virtual work. So what do? The little f, big F, L over EA for every member, pop it in Excel, and bam. Uh-oh. It fails deflection, right? It's deflecting too much, okay? So now what? How do we fix this, okay? There are oodles of ways to fix this. This is my advice for the most systematic way of fixing it. what I do is I look at this column, okay? And I'm gonna focus first on this member and this member. Why this one? Because these two carry the most energy in the whole truss, right? How do I know that? Because they have the biggest FFL over EA time. Okay, see where they're a W12 by 72? What I'm gonna do is take these members, make them one size higher. By the way, this is a wonderful calculation to do in Excel, right? So what I'll do is I'll take these members, make them one size higher, see if that worked. If that didn't work, okay, take the next ones, make them one size higher, check it again, and iterate over and over again. And I propose that if you do that a few times for this truss, okay, if you end up switching these members, these highlighted members, to these sizes, you'll get the deflection to meet the 2-inch limit, okay? And so graphically, what does that look like? It looks like this. So this one, this one, this one, this one, and then these two, I ended up changing a little bit higher to get me to meet that 2-inch deflection limit. So deflection actually governed the design for this bridge. In other words, like, we had selected members that were certainly strong enough to meet all the load demands, but it deflected too much. So we had to up our member sizes just to meet the deflection limit. So this would be a case where a service limit state governed the design, not a strength limit state. Strength limit state would be picking members based off of this. Service limit state would be picking members based off of deflection limit. Okay? Make sense? Last thing to do now that we have a truss is compute the weights, compute the cost. So the weight per foot, where do I get the weight per foot? The pounds per linear foot comes from the second number here. I have the member length in inches. Need to convert that to feet. It's going to be in inches primarily. I'm putting it in inches in here because it will probably be in inches in your Excel calculations when you do deflections. So just be aware of that. So pounds per linear foot times length give you pounds. Add up the pounds. $1.40 a pound gives you a price. Does that make sense? And then the only thing left to do past that is to draw it up. I even helped you out there. If you go to Blackboard, you will see in the supplemental files, I even gave you an example of what that should look like, you know, for this truss, by the way. You're going to have to do one for your own. But there you go. Oop. Okay. Let me take a step back and see how's everybody doing. I threw a lot at you. Do the ideas kind of make sense? Everybody kind of get the idea of the flow, what you're supposed to do, like what the overall goals of the project are. Make sense? Okay, so now let's talk about deliverables and what you are going to do for your project. Okay, so truss project constraints. This is what you all are going to do. Your truss geometry is going to be subjected to the following constraints. First off, you are going to have to lay out trusses. And for every truss that you lay out, you're going, and I'll talk about what that means here in a second, but IT's got to be 0. Okay? It must be a statically determinate truss. Okay? So you're going to have to come up with 3 options for a truss, and then you're going to have to verify for each of those options that IT equals 0 and it must be stable. Okay? Everybody with me on that? The truss will be simply supported at the ends. So you're not going to have to worry about IE. IE is going to be 0 by default. It's going to be stable and statically determinate externally. So what that means is no pier in the middle. Okay? There is a hinge, roller. Those are the supports. Okay? Everybody okay with that? This is important. Okay? So I want everybody's eyes up on here on this. In order to assess the deflection at the end, you need a joint at midspan, okay? So you've got to have a joint at midspan, okay? Let me give you an example of what I mean by that. When we measure deflection, we are going to measure deflection. This is the rule that we're going to use. We are going to take the central joint at the bottom, okay? So this truss, no good, okay? Because there is no joint right there, okay? But if you were in love with this truss, by the way, this truss wouldn't work, and you'll see why. But if you were in love with this truss, you could you could do this. Because now there is a joint there. Just take it and do that. Does that make sense? There must be a joint at midspan, okay? Everybody remember that. No individual truss member may exceed length limitations. I'm going to pull that up here in a second. So you have limits on how long each member can be, okay? The idea is that you're driving a truck with a bunch of steel through Huntington. You can't have a single truss member that's 120 feet long, okay? The members themselves have length limits, okay? And that is something I change every year. Okay? The truss also has an envelope limit, okay? So, for example, here's the support, here's the walkway, here's me, okay? There is an envelope. The truss must fit within this envelope, okay? And that, I'm going to use the term alpha in the handout. So like you could, let's say alpha was 12 feet. You could use like this option, but if this dimension was 15 feet, no good, okay? Because that's the limit, okay? Does that make sense? Everybody's gonna, there's gonna, the limit, and that is also a value that changes every year. But you can do bridges like this and bridges like this. You could have bridges with the truss over the walkway or under. Either one's fine as long as the truss fits within that envelope. Make sense? Your submittals. Let's talk about the submittals. So submittal 1, which is going to be due October 14th, I think it is. I'll pull it up on the handout here in a bit. You do not have to do a lot of work, okay? This is what I want you to do for submittal 1. I want you to come up with 3 truss layouts. Like, for example, this might be truss 1, this might be truss 2. Whatever. Come up with 3 of them. Each truss layout has to conform to the project specifications. Okay, each one. I want you to verify that for each truss IT equals 0 and all of that. Okay? I don't care if you draw them by hand. I don't care if you draw them in CAD. You can do it however you want, as long as it's neat. Okay? What you will then do is, for these 3 trusses, you will pick one. Okay? And you will tell me how you selected it. I'm actually leaving that part open-ended. Okay? So if you say, I want to pick this truss because it has the fewest number of members, that's fine. If you want to pick this truss because you like the aesthetics, that's fine too. If you come up with 3 and one's a really wild truss and you say, I just wanted a challenge, that's fine too. But I want you to develop a selection strategy for why you pick one versus another. If you do some research and find, I see a lot of pedestrian trusses that look like this, that's fine too, okay? But you must write up, and it's no more than a paragraph, tell me why you picked one versus the other. So if you come up with version 1, version 2, version 3, and you pick version 3, tell me why, okay? Because what I'm going to do is I'm going to ask you in submittal 2 to go back to that and go, hey, what would you do differently? That's why I'm asking you to do that. So far, so good? I want a single PDF. I need a sketch with every layout showing all the associated computations and the dimensions. And then I need the write-up as to why you chose the concept. That is what is due on October 14th. So to be crystal clear, no structural analysis, no cost estimation, no member iteration, none of that is due for submittal 1, okay? Just this, okay? So it's really not a lot of work, okay? Everybody get that idea? Now, here's submittal 2. Submittal 2, there's a lot to submit, okay? That's kind of the big one. You're going to take the truss that you picked and you're going to run with it, okay? In other words, you're going to do all of this stuff in that. There are a couple caveats though. You're going to analyze the trusses using Mastan. You haven't been shown how to use Mastan yet, so you couldn't do that anyways. That comes later, okay? And you are going to draw it up in CAD, the final truss, okay? So for submittal 2, you're going to select the truss members to meet both strength limitations and deflection limits, and you're going to compute the cost of an individual truss. Don't give me the cost of both trusses, just one truss line. For everybody's project, there's a truss here and a truss here. Just give me the cost of one of them, okay? So far, so good? You're going to submit in Blackboard 3 things. You're going to submit the CAD drawing. You're going to submit a set of associated computations, and you can do those in Excel, that's fine. And you're going to submit your Mastan file. We haven't discussed that yet. We'll get to that later. We'll discuss Mastan sometime in October, okay? How are we doing so far? Now, I'll pull the project up here in a bit, but here's my tips and tricks for you, okay? This is my advice. Truss symmetry is your friend. If you are not laying out a truss that is not symmetric, then you're having to analyze the whole thing and every member's different. There is no reason for it not to be symmetric, okay? Truss symmetry is your friend. Microsoft Excel is your best friend. Just point blank. You're going to have to do a lot of iteration, a lot of calculations, and there are some Excel tips and tricks that I'm going to give you that are going to make your life a little easier. Try and avoid a ton of zero force members, unless I guess it's part of the plan, but a bunch of zero force members might not be the best idea. It might be, might not be. I tend to say avoid them. Use the IT expression to help develop your geometry. In other words, if you know how many joints that you're going to use, you can sort of like back calculate how many members you should have. This is more for submittal 1, okay? Don't be afraid to be creative. There is no requirement that your truss be a certain cost or be a certain meet a certain cost threshold. Okay, there is no requirement. But I do have sort of a friendly challenge for you. That's how much mine costs. I challenge you to do better. I'm not saying that this is the best answer, and I truly believe that some of you could come up with a better cost than this, okay? But that's my cost. I want to see if you can do better.
And what do I get if I do?
A thumbs up and a handshake. Again, it's not for anything. All right, hold on, we're not done. All right. Okay, so this is the actual project handout, and if you look at the bottom, these are the project parameters this year, okay? These change every year, okay? Every year they're different, okay? So our truss this year is going to be 120 feet long. The walkway width is going to be 24 feet. The load is 950 pounds per square foot. You are still limited to W12s. I'm going to do an allowable stress of 32 KSI and a deflection limit of L over 400. So take the length divided by 400, that's the maximum deflection. We're going to go with $2.18 a pound for steel. Again, IT must be 0. The truss is simply supported at the ends. The truss must contain a joint at midspan along the bottom of the truss. Right here. No individual truss member may be longer than 22 feet, okay? And the envelope, alpha, is 16 feet. It is a 16-foot envelope, okay? Last thing I'll show you before I'll pull up the code one more time. If you go to Blackboard, you will see in the supplements section, supplemental files, you will see, bless you, this Excel file. This Excel file contains all this data. So it's all referenceable in Excel. So you don't have to like type all this out, okay? I gave you the entire shape database from the manual just in case you want it, but really what you'll need is this one. Sound good? Any questions? I'm gonna pull up the code one more time. If there's handouts over there in case you didn't get it, but have fun.
We're assuming it's just horizontal, right? As well.
What?
We're assuming it's just completely horizontal.
It's a flat truss. Yeah, no, nothing at a slope. Flat.